Okay, so I want to talk about today about switching a little bit from LLMs to other models. So I guess my talk will be try to convince you that we should develop alternatives as well. And at the same time, I'll try to convince you that if we develop alternatives, we can get a lot of new insights. Also use those models to facilitate scientific discovery. Okay. So we understand the world around us pretty well, right? So far, but there are still many things to be discovered. And for the first time in history, probably, we have an artificial intelligence that helps us with that. So that's exciting. And I think interpretability is really the new frontier. And we talk a lot about it, but I think one of the outcomes of interpretability can be discover new patterns in data. I'm going to showcase one or two examples today. But the idea is that we leverage the power of LLMs and combine that with insight into them, or power of artificial intelligence models, combine that with insight into them and try to find new patterns that we didn't know before. So causal insight for any data type is very important to me. Okay, so we have LLMs that are great, and I don't disagree with that. But to me, they test more basically the frontiers, or what can emerge. Test the limits of what can emerge in a neural computation, and they're very difficult to interpret, right? They are giant. The ones that perform good are giant, and so we maybe have these in behavioral interpretability where we can test these models and explicitly and ask them questions directly. But I want to make a case for building alternatives to that, more realistic model of humans. So to answer the question, how do properties emerge? How do we humans learn language? And because these models that I'm going to show are smaller and they're based on CNNs, not on transformers, they're more interpretable, and they can provide us with crucial insights into new data types. And I'm going to give you a couple of examples from neuroscience and from animal communication. But the idea is that we can do scientific discovery with these tools, which is exciting. Now, speech is great for that. I work on speech, and speech is amazing because it's a continuous data. It's physical, measurable, continuous data. Brain imaging is very easy on spoken language. It's less complex than vision. A lot of work, obviously, is on vision. And humans have innate generator, right? We have spoken language generator. Our mouth and articulators are our innate generator, which we don't have for vision. We don't generate our imagination, but we do talk a lot. And so this is innate, and we've been studying language for a while. And if you think of it, phonemes, right? The thing that speech scientists have been studying for a while are the first mental representation of a continuous measurable physical space, right? Phonology is what basically deep neural nets do. They have some continuous measurable space, and then they represent it with representation learning. So speech is great. Another thing that's great are animals. And we've been asking a lot of this question, like, can scaling lead to an AGI, right? And that same question has been asked in animal communication for a very long time, or like comparative animal behavior. Are we just very smart animals, or is there something uniquely human about us that allows our intelligence and whatever we came up with over in history? So there are two sides of the exact same debate. Okay, and we can learn a lot from history of these fields and from each other. Okay, so first step, let's try to create a more realistic model of human language acquisition. So this was already brought before. No baby learns from text. No baby learns from gigantic amounts of text. No baby learns without the listening and speaking. And this is a production perception loop. And no baby learns without communicative intent. So how do we actually learn, and how does speech process work? We have some information. I have some information. I move articulators. I actually do muscle movements. So sign language and spoken language are not that different. It's all muscle movements. Muscle movements of my articulator results in sound. that sound carries an information. You decode that information from the sound, and hopefully my information, your information match, and we are speaking and communicating. So we've been building this, hopefully the most realistic model of human language learning so far, which has a couple of components. It's all deep neural networks, but they're convolutional neural networks, which are biologically maybe more inspired, but more realistic and way more interpretable than transformers. And the idea is that we have a generator, a model that speaks, that takes some information, we model information in theoretic terms. So there's a bunch of codes and a bunch of variables, and it learns to move articulators. And those movement of articulators get transformed into sound, and that sound travels to two components. One component is discriminator, which forces imitation. So it's learning by imitation or imagination. And then the other component is decoding, right? So we have production perception loop. This guy needs to look at the spoken output and decode information from it. So here's some unique information. It gets encoded into sound through articulators, and then gets decoded by another network that represents auditory processing, so word classification. So this is now basically language as informative imitation, right? So learn to approximate what you hear from parents, but also learn to produce spoken language such that it carries information. And all of this is completely unsupervised, just raw audio, no other data that we're feeding the models. And so we think that this is a more realistic model. We're trying, we're adding steps, like we're adding parents and stuff like that, vision. But there's a lot of advantages of these models. It's completely raw sound, fully unsupervised. This is learning by imitation, imagination. They're very innovative. I'll show you later. The basically production perception loop is baked into the architecture, right? They need to listen and hear and produce, and that's how they learn. Basically, production is essential for learning. The generator never sees the data directly, so it's extremely innovative. They have the kind of traces of communicative intent, and we show that disentangled symbolic-like representation emerge in these models, which is nice because we have these interpretability techniques. And you can compare these models with human behavioral and also human neuroscience. So there's a lot of levels we can model with these models. And it represents like this early language learning, right? Where kids get a few words and they need to learn to move articulators, and what do they do when they do that, and so on, how they learn, how they approximate learning in humans. And we can look inside these models. This is very important. Looking inside these models is very important. So we have this technique that's actually relatively simple, but allows you to basically understand how these models encode whatever is meaningful in language, right? So we know that words are meaningful, morphophonological processes are meaningful, sounds are meaningful in language. And so what we do is in the latent space, in the final layer of the generator, we can find variables. We can find variables that correspond strongly to some property in language that we're interested in, and we can force that variable to be in the output. So the technique is called extreme value interpolation. Basically, during training, your latent space is limited to some interval, but if you take a single unit and stretch it to extreme value, you find a causal effect between a single unit and something that is meaningful to you as a linguist, which is great. To my knowledge, that doesn't exist yet in transformer, but this causal relationship between single units and something that is meaningful in language is very important and very powerful for understanding these models. So you can take a single variable and take an S in and out of the output, for example. You can take a single variable and take some morphophonological process like reduplication, which is very complex. Pipiro goes to Piro, right? So it's not just concatenative things that these models can do causally. Just take a single variable, stretch it to extreme values, and interpolate and observe the causal effect between something that we know is meaningful in language and that single variable. It learns words really well. Which is nice. It learns to produce new words. That was the coolest thing, probably the output, which is the model was trained on 8 words, and it started producing new English word that it never heard before. It says start, and it's and other carrot and so on, dust. And it was only trained on these words. So it starts to learn phonotaxis and combine sounds into meaningful things. And you can now bug test. You can zero-shot test how these models will learn, right? We can give it reduplication, but withhold some S initial word and say, okay, reduplicate it, right? So you stretch one value, say reduplicate it, and then BS initial word. And so you see how rules emerge. And is this kind of relationship between these variables, which is nice. And I'm glad that other labs have started taking on these models, and they have really good results. For example, they show the French nasalization is differently learned than English nasalization because it's compositional, and it's contrastive in one and the other, and so on. And we also show that we learn articulators in a similar way as these models do. So the models actually learn to move mouth in a similar way as humans learn to move mouth when they start speaking. Another nice thing about these models is that, as I mentioned, we can look inside them. These are convolutional neural nets, way more interpretable. And we have this technique from 2022 where we can look inside the models and do a very similar thing that neuroimaging does, electrical EEG, for example, which is summary of electrical activity in time domain, right? What we do is we look at each of these internal convolutional layers, we summarize artificial activity across layers. CNNs have feature maps based on filters. So I could talk about this at the discussion period, but there's a very simple technique where you can basically understand how the model creates spoken language outputs or inputs. Okay, so you can go layer by layer and see how each layer, what it encodes and how it transforms some information into spoken language through these more and more abstract or less and less abstract layers. So see how this abstraction goes up. This is a monosyllabic word that becomes a disyllabic word. And you can see that deep in the layer, acoustic envelope is encoded, but later on, the fine grain stuff is encoded. So this ability to look inside acoustics is very useful for comparison between the brain and these artificial neural networks. And there were amazing talks already, but this is different because these are not transformers. But I think that's in some ways an advantage because, as I mentioned, CNNs are more interpretable and maybe biologically plausible. So what we did was we trace how we hear sounds. And when we hear sounds, the signal travels through brainstem and then onto cortex. And we have this thing where we can auditory brainstem response is a technique where you can catch signal in very early on in the brainstem. And actually, we showed that if you send this exact same syllable ba to humans in a EEG experiment and to our models, you get this really similar time series response. And to the degree, none of this is actually transformed. We don't train a linear model that predicts one sound from another. This is basically internal representations in CNNs are just very similar because the way we need to process sound is probably similar. And so, to my knowledge, this is the most similar, the closest raw similarity between the ANNs and the brain. And we have a follow-up study where we show that later on, stuff deeper in our model representations are very similar to cortical data as well. So ECOG data that's not published yet. And there's a lot of downstream stuff that you can do with this, right? So now that you have this raw comparison, there's no intermediate steps. You can basically you can train a model, a Spanish and English model, or test for sensitivity period, or compare English, Spanish trained and English and Spanish speakers, and how the representations differ. Because we know that a lot of phonology is already encoded in the brainstem and so on. So there's a lot of possibilities. You can, train models on music and on sound and on speech and see if tonal processing is better. You can test, monolingual Mandarin speakers and how the sensitivity period work as they are encoding different contrasts in language, and how that gets encoding in models as well. Okay, so now that was neural stuff. I think it's very useful to have the idea of neural, the comparison between neural representations is more realistic CNNs. Now we want to understand how we basically built an all-purpose pattern discoverer. Our artificial baby finds patterns in language. We have ground truth in language. That's great. Can we use it to on other communication systems? Now, this is a case study where the important thing is we can interpret these models now, right? We can look inside them. Can they solve some of the hardest problems out there in science? So we have sperm whales, and they're amazing creatures. And they also communicate, but they communicate with these clicks that sound like Morse code. And for longest, this was considered a Morse code type communication system. But we trained our model. We trained our baby language learner. Of course, we removed them out, but we said, okay, learn to imitate whales and learn to imitate informatively and encode information into their codas. And then we went and checked what acoustic properties did you use to encode information in whales. And that doesn't mean that that's going to be meaningful, but it has a good potential to be meaningful. So sperm whales are these amazing creatures that I haven't seen anything like that in animal kingdom. They talk to each other a lot. Oh, the sound is not great, but they click and they exchange those clicks in conversation, and they put clicks into units of clicks that are called codas. And again, it was like, consider a Morse code, like click, 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 versus click, 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 and so on. So what we did was this was the traditional classification, and we take our GAN and ask it, learn to imitate and learn to imitate informatively. And then we have the technique where we take that extreme values, pair it with statistical causal inference, and understand what did the model encode, okay? What did the model consider meaningful with these interpretability technique? And so when you do this causal inference with extreme value, the composition, you see that some bits encode meaningful things. And number of clicks was shown to be meaningful. Timing was shown to be meaningful, which is great because those things are most likely meaningful. But we also discovered the model predicted that spectral properties will be meaningful as well, okay? And then we went and checked, and we did not know that at the time that the spectral properties are meaningful. But we found something that was actually quite surprising. We found that sperm whales have pretty much analogs to human vowels. How does that work? When I say an ah versus an e, the difference between ah and e is that for ah, I open my jaw. For e, it's much more closed. But you can hear the difference between ah and e, even if you don't see me, because on the spectrum, you have different bands of frequencies form, right? Different form and form. So in ah, they're close together. In e, they're far apart. Now, that doesn't seem, these are the formants. That doesn't seem anything like the clicks of the Morse code of whales. But our model said, no, this is meaningful. Spectral properties are meaningful. So we had, it required ourselves a lot of time to figure out, okay, maybe their timing is wrong. The timing in the clicks is very different from our timing, and the timing in sperm whales is very different. So we started cutting timing between those clicks, and if you do that, we started observing a very, very similar pattern to human vowels. So those sets of clicks that I put into codas not only have different timing patterns, but spectrally, they behave like human vowels. And you have a very structured discrete type where one coda is either one type that has two formant frequencies or the other type that has only one formant frequency. And they exchange that, and it's never a mix, never a mixture. So it's very controlled, very discrete, very structured. And they exchange those vowels in conversations back and forth when they talk to each other. And you see these other patterns. Sometimes the patterns, they're beautiful patterns that we didn't know existed, but they're probably meaningful. We don't know what the meaning is, but they're very controlled. It's not some sort of automatic movement thing. It is a pattern that we didn't know, but our model predicted. And then we check, and actually the way they produce these sounds is very similar to how we produce sounds. It's a case of convergent evolution where our clicks are vocal fold vibrations. And then we have the formant frequencies that we modulate with the shape of our mouth, right? Ah versus E. In their communication system, their vowels, their clicks are produced with the phonic lips that are very similar to our vocal folds. And then on top of phonic lips, we realize they have an air sac. And that air sac acts as a resonant body that changes the resonant frequency. So basically the effect is the same, right? You have the source, which is either vocal folds or the phonic lips, and then the filter, which causes these differences in spectral properties that is either our vocal tract or their air sac. And so this is a nice case where literally, I gave an interview here at the time where I didn't know yet. We didn't observe the patterns, the vocalic patterns yet, but the model already predicted to be there. And it was funny because I gave this interview right at the time where the model predicted the spectral properties to be meaningful, but we didn't find them yet. So it is literally a nice case of where you can take a custom-built model that you understand well and transform it to train it to another data you have no ground truth about to help you discover new patterns that you didn't know before. Okay, so I have to talk about LLMs as well, not only whales and brains. So the one thing that I'm really interested about LLMs, as I mentioned, is that they test the kind of the limits of neural computation. What can emerge in a neural computation, right? And if I'm interested in animals and humans, I'm also very interested in what is uniquely human about language and what makes it possible and so on. And what are the few aspects of human language that are not possible in animals, or they're not present in animals? And they're not many. Animals can do symbolic reasoning, animals can do a lot of things. Recursion and probably this kind of meta-linguistic, metacognitive abilities are a couple of important things. And so the reason, that's the reason why we wanted to test LLMs and their abilities on those two tasks, right? So I'm really interested in whether LLMs can do recursion, explicit recursion in this case, and whether they can do metacognitive abilities. So what we did was actually quite unusual, and maybe it goes into the try to shock type of experiment that was mentioned by Adina, I think. But well, now that you cannot really look inside these networks, either because they're closed or because they're too big, you have to find some ways to try to understand what their internal abilities are. And one of the things we did is we tried to use just syntactic formalism to see whether they can do metalinguistic, whether they can do metalinguistic tasks, right? And the nice thing about syntactic formalism is that it is very, very present in the training data, and it can offer a nice window into abilities of these models to do language internally. So we asked the model whether they can do the sentence, the mouse or the cat or the dog painted, Todd sang. And not only that, we asked it, draw a syntactic tree about it. And for the first time ever, GPT-4 was able to do this in a B+, A- kind of way for considering a graduate student. So this, seems like a weird task, but the more you dig into this, it is a very efficient way to test the abilities, because not every model can do it. And the ones that can do it pretty well, and can perform both on various different tests. And 3.5 didn't do it well, but 4 does it well. And you can make up new sentences and try to control for memorization, and it does it well there as well. If I fed my baby turtles, recognize the structures. In German, it can do what has Han gesagt, that has gestern gegessen hat. So what did Han say that he ate yesterday? So there's a lot of things that you can test. There's phonology so you can use phonology, which is a little bit better than syntax, because you can come up with an artificial language that is definitely not part of training data, and you can test this in abilities of these models. And then we also tested the recursion. So you can give the model a recursion, ask it, is this recursion, and then ask it to add layers, and it does pretty well there. So I think there are many pitfalls. Of course, this was already mentioned, but I think the important thing is that LLMs have this ability to test the limits of computation, what can emerge in a neural computation. And I think these linguistic formalism of all the things is a useful tool to look inside them. So these are our papers. So to conclude, I think LLMs are great for, as I mentioned, testing the abilities. And unfortunately, we have to do behavioral interpretability until we find this better ways to look inside them. But I think it's really important to also develop and just work on alternatives that are more realistic, that are more interpretable, that can be compared to brain better. And at the end of the day, the exciting thing now is that I think we live in a time where AI and humans can inform not only ourselves, but we also have a way to try to understand better what animals, how they communicate, and how their systems work. And I think we're now at a world where we have 3 players: humans, animals, and machines, and they inform each other mutually. And I think there's a lot to be learned from all these systems. Thank you.